Welcome to the best resource online for learning Python. By the end of this crash course, I will make sure that you learn and master Python programming. Before we dive in, you might be asking yourself, why should I bother learning Python? Mastering the Python language is a great skill to have, mainly because it's a general purpose language, which means that it's designed to be used for creating all sorts of different programs. It can be used for game development, web development, and even data science. So it's really important that you're able to read and write Python code. In this first section of the Python course, you will familiarize yourself with the main building blocks of Python. So let's jump into our first lesson. In this first lesson, we'll start off easy and look at basic arithmetic operators in Python. The first operator is the addition operator, which is performed by the usual plus symbol. Hence, printing print 1 plus 1 should give us 2. On a different cell, one thing to note about the Jupyter Notebook application is that to see the result of an operation, you don't always have to print it. You can simply declare the Python operation like so, 1 plus 1, run it, and it should still show you what the output is. Except now, notice that when you print it, it doesn't show the out text. Whereas in this case, by removing the print statement, it does. What does that mean? Well, if we were running this code on some text editor, which is what we're going to do in the near future, to see the results of the output, let's say on the terminal or command prompt, we would have to print it. Simply declaring the operation won't tell us anything about the results. In the case of Jupyter Notebook, simply running the code inside of a cell without printing is enough to tell us about the output. Not a major point, but good to keep in mind. Another arithmetic operator is subtraction, which in Python is denoted by the usual minus sign. Therefore, 1 minus 1 should indeed give us an output of 0. Multiplication, as you've guessed it, it is denoted by the asterisk. Therefore, 7 times 7 would give us 49. And division in Python, as you've also guessed it, is denoted by the slash symbol. No tricks there. So 10 divided by 5 gives us 2. Another important thing to note is that Python follows the order of operation. For example, if I were to print 6 plus 9 times 3 plus 3, the output would be 36. Since as per the order of operation, multiplication must occur first. 9 times 3 gives 27. Then you add 3 and 6 to give 36. If you want to ensure addition occurs first, just like you would in everyday math, place brackets around 6 and 9 and brackets around 3 and 3. Adding 6 and 9 to make 15, adding 3 and 3 to make 6, multiplying 6 and 15 to give 90. This is just basic mathematic order of operation. But let's also talk about the modulus operator, denoted by the percent symbol. The modulus operator simply outputs the remainder of a division. For example, 6 modulus 2, if we run this, should give us 0, since dividing 6 by 2 gives a remainder of 0. 9 modulus 2 would give an output of 1, since 9 divided by 2 gives a remainder of 1. Now what about exponents? A common mistake is to use the caret symbol for exponents. In Python, this is incorrect and represents a bitwise operation. We'll look more into it later on. To denote exponents, we use a double asterisk, such that 6 double asterisk 2, 6 to the power of 2, if you run it, obviously 6 to the power of 2 gives 36. Finally, the last operator I want to talk about is the double slash, which divides but also rounds down to the nearest integer. So 13 divided by 2, as you know, is 6.5, but if you run this, it rounds down to 6. That's all for arithmetic operators. Nothing scary so far, just simple mathematical operations that are commonly done in Python. In this video, we'll further inside of Jupyter Notebooks, we'll create a variable labeled age is equal to a value of 25. If you output this variable, this value, and run it, indeed it gives us 25. The equal sign is an assignment operator that assigns the value on the right to the name on the left. For the purpose of concision, Python also lets us assign multiple values to multiple variable names. For example, what you would do in another language is write age is equal to 25, name is equal to Jane, and gender is equal to female. With Python, you can use the comma operator to assign all three variables at once. That is, I can write age, name, and gender is equal to, make sure everything is in the proper order with respect to your variable names, such that age will be 25, name will be Jane, and gender female. Only use this notation with closely related variables. For example, all the variables here represent the characteristics of a person. You could also do this with dimensions like width and height, as they both represent the dimensions of some shape, most likely a rectangle. Try to keep your variable names as descriptive as possible, to ensure that you're always aware of what's going on in your code. For instance, you can never have any space in between. If I'm to assign blood type is equal to AB, I can't actually do that. If I try to run it, it should give me an error. In such a case, you would want to use an underscore to separate your two words, like so. Blood type is equal to AB, and this should run just fine. Also, only use letters and numbers in your variable names. Don't use symbols like $sign or modulus. As a convention, all variable names should be lowercase and have an underscore in between. Do not capitalize anything as you would in camel case. Always use the snake case, which connects all words with underscores. Finally, there are certain keywords in Python that you cannot use as variable names. They are reserved since they carry very specific purposes in Python. You'll learn more about them throughout the course, but words like return, while, or import are reserved words. You'll learn more about them as you progress through the crash course. One thing to also note about Pythonic variables is that you can assign them a new value. Storing a new value to a specific variable erases the old one. For example, let's assume that 5 years later, Jane is now 30. I can reassign this variable age from equaling 25 to age is equal to age plus 5. If I print this, it should give me 30. So we took its current age and added 5. Perfect. This also introduces the plus equal assignment operator. The plus equal assignment operator, you've probably seen in other languages, is a shorthand operator which lets us express the operation more cleanly, without having to write the name of the variable twice. Basically, what we did here was take the current value and increment by 5. Similarly, we can write age plus equal 5, which once again takes the current value of the age and adds 5, but does it more concisely. If I output the value of this, it indeed increments it by 5. There is a similar operator, the minus equal operator, which, as you guessed it, lets us decrement numbers. So instead of writing age is equal to age minus 5, let's assume for whatever reason Jane is getting younger by 5 years. Instead of writing this out, you can simply write age minus equals 5. And what that will do is decrement our age by 5 every time. What we'll do is actually go ahead and print out the result of the output, and we get 30. That is all for variables. Pretty easy stuff so far. It just takes a little practice to get used to, but the concept should be very straightforward. Now we'll look to enhance our understanding by exploring numeric data types. So far we've looked at whole numbers, or integer values, such as x equals 7. We just assigned x an integer value of 7. Let's also assign y an integer value of 3. And now simply set z is equal to x divided by y. And we are going to output print z itself. This gives us not a whole number, but a float value. A float value uses a decimal to account for numbers with fractional values. That said, there are two Python data types that are used to denote numeric values: int for integer values and float for decimal values. Int and float. Int and float, since they are two different data types, will therefore have different operators and functions that work on these objects. We can use the type function to determine the data type of a certain value. For example, we know that x is for sure an integer, since we assigned it an integer value of 7. Let's test it out. Print type of x. And this prints out an integer type, which is what we expected. If I make this 7.0 and run the cells, it prints out floats, because now it is indeed a float value. A mathematical operation between an integer and a float will always produce a float. For example, 2 plus 2.5 gives 4.5, a float. 7 divided by 3.5, although mathematically this should give us just 2, the division operator is a special case, as it always results in a float value whether we're dividing by an integer or a float. So it will give us a float value of 2.0. If you print the type of the result of this operation, it will be indeed a float, as demonstrated. However, let's assume for whatever reason that you absolutely needed the product of this division to be an integer type. To convert this float numeric type to an integer, we can do so with the following syntax, by wrapping it with the integer data type. What this does is it will cut off everything beyond the decimal. So instead of 2.0, this will just be 2. And indeed, that's what the output reflects. If I set w is equal to an integer of 3.7, it's going to cut off the 0.7, and by outputting w, it will give us a value of 3. This can be useful if you are counting the number of people that voted, for example. You can't have 3.7 people, it must be a whole number. So the take-home message, if the result of the computation relies on an integer value, make sure it's an integer like so. Accordingly, you can also convert an integer to a float by enclosing a variable with the float data type, which will simply add the decimal 0.0 to make it into a float value. So set some float is equal to a float of 3 and print some float. By doing so, we get a value of 3.0. Alright, that is the basic gist behind integer and float types. You'll come across these data types very often throughout this course, so it's very important to be aware of their distinctions. Previously, we covered numeric data types, float, and int. Oftentimes in Python, we'll have to work with text, in which case we'll be dealing with string data types. The simplest definition I can come up with for a string is a series of characters, enclosed by either a double quote or a single quote, both of which work equally well. For example, set name equal to Amir. Print the name, and print the variable type. Print type name. If you run this cell, it gives us a string type str. If I replace Amir with double quotes Amir, it should work the exact same way. It outputs the same result, and it's still a string. However, there are some cases where one is advantageous over the other. For example, what if I wanted double quotes inside of my string? How would I do it? Let's try this. Set dialog equal to Amir said, "Hello, John." To which John replied, "Hello, Amir." All we have is a string with some dialogue inside, the dialogue indicated by the double quotes. If I try to run this, I'll get an error. There are two solutions to this. Instead of writing the string with a double quote, use a single quote. And you should be good to go. That way, you can use double quotes inside of your string. Let's run this. And everything works out fine. Let's assume inside of that same string, I wanted to use single quotes as well. That is, instead of John saying, "Hello, Amir," he says, "You're the best." You're the best. This doesn't work. You can't have single quotes inside of a single quote string. Not like that, at least. Unless we use a backslash in our string to include this quote. You're the best, like so. Print it, and we're good to go. If you don't put the backslash, Python is going to think that this quote is what ends the string, and everything after it is extraneous. By putting the backslash, you're telling Python this quote is part of the string. It's not ending it. A common operation in strings is to concatenate them. We can concatenate strings. We can add strings the same way we added integers and floats with the plus operator. For example, set a variable segment1 is equal to I am 25, and set another variable segment2 is equal to years old. We need to concatenate these two strings to make a full sentence. What we'll do is we'll write full sentence is equal to segment1 plus segment2. If I print this full sentence, print full sentence, they are indeed concatenated, except we need a spacing in between them. So in between the two segments, we'll also add an empty space, plus empty space, and plus the segment number 2. And this achieves spacing in between the two strings. What's interesting is that strings can also be multiplied. For example, if I am a parrot and I want to repeat the sentence 10 times, simply print full sentence times 10. Output the result, and we get exactly what we expect. It repeats 10 times. Let's actually go ahead and set full sentence times 10 equal to a variable long sentence. Long sentence is equal to full sentence times 10. What if I asked you to count all the characters in that long sentence? That would take you a while. Well, I mean, you could just count the characters in this one sentence and multiply it by 10, but that's not very fun. Python has a useful built-in length function that returns the length of not only strings, but collection types as well. We can obtain the length of this long string by using the built-in function len for length, which takes in our long sentence value, long sentence. This length function will return the length of the string, so we'll just make sure to print it, output the value, and we get a value of 170. So far, we've only dealt with built-in functions like len or print that perform a specific action. This prints a value, and this returns the length of an object. Soon enough, we'll learn how to build our own functions. So far, we've looked at integers, floats, and strings. Now let's look at Boolean types. In the most simple terms, a Boolean type can have one of two values, true or false. That's it, no tricks. How do we assign Boolean type variables? Simple. Let's look at an example in Jupyter Notebooks. This crash course is awesome. We'll set that equal to true. Obviously, I'm a bit biased. And this crash course is not awesome. is equal to false. There you go, Booleans in a nutshell. For starters, I highly recommend your variable names be a lot shorter than this. But regardless, we'll go with this for the sake of example. Can this get harder? Of course. The way I just assigned these Booleans isn't very useful. Normally, comparison operators like less than, greater than, less than or equal to, greater than or equal to or not equal to, these comparison operators are often used to produce, to return a bool value, instead of us hard coding something to be true or false. For example, if I set comparison operation is equal to 1 is greater than 2, and I print it, print comparison operation, it gives back false, because indeed 1 is not bigger than 2. That is a false statement. If I replace it with smaller than, it gives back true. Along with comparison operators, we can use logical operators. The three logical operators we'll use are and, or, and not. Let's start with or. If I set comparison operation equal to 1 is smaller than 2, or 2 is smaller than 3, this gives back true, because indeed both comparisons are true. 1 is smaller than 2, and 2 is smaller than 3. If I switch this to 2 is bigger than 3, even though this expression is false, even though we know that 2 is not bigger than 3, this entire operation will still evaluate the true, since with the OR operator, only one of the expressions must be true, and indeed this one is. If I run this, we indeed still get true. However, with the AND operator, if one of these conditions is not true, then the value will return false. Both the first expression and the second expression, they must both be true. We can prove this by running the code, which prints out false, and makes sense, since both comparisons must be true with the AND operator, and indeed this is not the case. 2 is not bigger than 3. However, with the OR operator, as long as one of them is true, then it returns a value of true. The last logical operator we'll look at is the NOT operator. What this does is it flips the bool value. For example, set comparison operation is equal to 1 is smaller than 2. We know that this is 100% true. We know 1 is smaller than 2. But if we add NOT, it flips the bool value to false, giving us false. That is all for Booleans. So far, we've covered 4 fundamental data types: Booleans, strings, integers, and floats. Now we'll be looking at built-in methods. Previously, we've looked at built-in functions. Functions like length, type, and print. All of these are functions. They accept arguments or argument inside of their parentheses. How is a method different from a function? Every data type has its own distinct set of methods. For example, let's focus on string methods. Back to Jupyter Notebooks, declare a string movie title is equal to Harry Potter and the Prisoner of Azkaban. Great movie, by the way. Anyway, this string variable has its own distinct set of methods. These methods, as opposed to functions, can be accessed with dot notation. A string data type has over 60 methods that we can access. Let's focus on the more common ones. For example, the upper method, movie title dot upper. What this method does is it takes the string variable and it returns an uppercase string. If you print movie title.upper and run this cell, indeed it prints an uppercase string. To make this a lowercase string, simply write movie title.lower. This is another built-in string method. Run the cell, and we get a lowercase string for every single letter, even the first ones. So, take-home message, every data type has its own distinct set of methods that are specific to it that can be accessed with dot notation. If I tried to use the lower method on, let's say, an integer, for example, it wouldn't work because the built-in lower method is not available to integers, only to strings. Some methods also take in arguments. For example, there's the count method. If I write movie_title.count, and I want to count the amount of times the letter A shows up in the title, so A, run the cell, and it gives back the calculated result. A shows up 4 times in our string. There are a lot of built-in methods. We're not going to go through all of them. That would be a waste of time. The message that I want you to take home is each data type has its own distinct set of methods. And all of these methods, depending on your program's functionality, can be found in documentation, or better yet, on Stack Overflow. That is all for built-in methods. And we're going to introduce list data types. The most basic data structure in Python is the sequence. A sequence is composed of elements. Each element has an index that indicates its position. The first element would have an index of 0. The second has an index of 1. The third, an index of 2. So on and so forth. This index represents the location, the position of an element. The most common sequence types in Python are lists and tuples. For now, we'll just focus on lists. Lists are always written in square brackets. If I want to declare a list of names, I would simply write names is equal to John, Jane, and Joe. John would have an index of 0, Jane would have an index of 1, and Joe an index of 2. How do I prove this? Well, I can access specific elements inside of this list based on its index. So, let's say I want to access the element at index 0. This would simply be names, open up brackets, and we want the element at index 0. We're going to print this and run the cell. As expected, the output gives John. At index 1, write the number 1, and as you've guessed it, we would get Jane. So on and so forth. Since we're able to look up individual elements based on their index, we can claim that this list is ordered. Overall, a list holds data. It holds elements, and all these elements are separated by commas, such that an element is accessed according to its index, since this is an ordered list. If you try to access an index that's beyond the range of your list, for example, an index of 100, when all we have are 3 elements, Python will yell at us, telling us that the index is out of range. Now it's important to note that lists don't have to contain a single data type. It can contain all of strings, floats, integers, and booleans at the same time. For example, set random variable equal to true, false, hello, 1, and 1.2, containing all of the data types we've talked about so far, and this would compile no problem. Just like strings, you can also get the length of a list. This list has 5 elements, so if we print length of random variable, as expected, it outputs a length of 5. Very often, the length of a list is used to access the last element of a list. How would I do this? First, let's set length. Or you know what? Let's do it on the same cell. Let's set length is equal to length of a random variable. Would I then simply write print random variable and we'll access the index at the length like so. Try to run this. This is not the error I was expecting, and that's because we have to run this cell first. And then if I run this cell again, it should recognize the variable length, and it tells us that the index is out of range. Why? Well, think about it. The length of the list is 5. The first element has index 0, second 1, third 2, fourth 3, and fifth element has an index of 4. So what can we conclude? The index of an element corresponds to the position of the element in the list minus 1. So we can retrieve the last element by reducing the index by 1. 5 minus 1 gives us 4, which corresponds to the last index in the list, outputting the desired result, 1.2, the last element. Alternatively, we can index from the end of the array by using negative values, where negative 1 represents the last element. Let's try it out. And indeed, we still get that result. Much easier. Minus 2 is the second to last element, which is 1, and indeed that's what's outputted. You can try it for minus 3, and we get hello. That's pretty much it for lists. If you come from another programming language, you'll find them very similar to arrays. And we looked at the list data type, which contains a sequence of elements enclosed in brackets. Since these lists are ordered, their elements were accessed based on their index in that list. We'll look at how we can access more than one element from a list by slicing. Slicing is done with a set of indices which specifies a range, the start and stop. The start specifies the index where we want to start slicing the list. For example, if I specify the integer as 1, it will start slicing the list at index 1. The stop integer specifies the index until which we want to stop slicing. If I specify a stop integer of 8, as soon as it reaches the 7th index in the list, it's going to stop. Notice how I said the 7th index, not the 8th index. That's because the upper index is exclusive, meaning the slicing stops at that index minus 1. It's not included in our sliced segment. In this case, our lower index is 1, the lower index is indeed inclusive, and our upper index is 8. So what this will do is it will grab everything from the list at index 1 up until index 7. Let's try this out. Back to Jupyter Notebook. Declare a list ordered numbers is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There is actually an easier way to specify a list of numbers with the range function. I'll show you how to do it momentarily, but we'll just stick with this for now. And let's assume that I want to grab elements from 2 to 9. How would you do that? Well, what we'll do is we'll write out the variable ordered numbers, and to specify indices of the list, remember we need the brackets. The lower inclusive start index will be 2, and we want everything up until and including the number 9. So our stop index will be the number 10. Remember, the number 10 is going to be exclusive, meaning the slicing stops at that index minus 1, so at 9. Let's output this. Well, let's print it first and foremost. Run the cell, and we get a list that goes from 2 to 9, a sliced list. Let's assume you wanted everything from 0 to 9. Well, you can specify the start index as 0, which will take everything from index 0 up until 9. Alternatively, there is a shortcut where if you omit the starting index, it assumes that you're going to start at the very beginning of the list up until your stop index minus 1. Let's try it out. And indeed, we get the same results. Let's put 2 back as the start index. So it's going to start at index 0, 1, and then 2. And from that index, we want everything on the list, up until the very end, from 2 till 10. We could simply write 11, which is the length of the list. Or if you want to get fancy, we could use the length function to obtain the length of ordered numbers, which indeed is still 11, therefore signifying a stop index of 11. But there is actually a shortcut to this. If you just omit the stop index completely, let's go ahead and do that. It automatically assumes that you want everything in the list beyond your start index. When you run the code, indeed we get the same results. This is perfect and much more concise. If you omit both the start and stop index, it'll just grab the entire list. But then again, why even slice in that case? Before moving on, I did promise that I would show you how to create a list of numbers in a more concise way. We can use the range function. That is, specify a range, and the range will be from 0 to 10. This will create a range from 0 all the way to 9. Even here, the stop index is exclusive. It stops at the number previous to it. And now I can wrap this up in a list data type. If we print it, print the list, it outputs a list in the range of 0 to 9. Super easy and much more concise than actually writing it all out from scratch. We can actually go from 0 to 100. As expected, it gives us a list from 0 to 99. Imagine writing all of this out and hard coding it. That would take a long time. If you don't specify a start index, Python will just assume a start index of 0. So if you omit this 0, we should get the same results. And indeed we do. Let's put this back, as we can also indicate a step size as our third argument. We'll put in a step size of 5, such that it will indeed still contain numbers between 0 and 100, 0 to 99, but it will only include every 5th number in the sequence. If we run this, clearly it does so in a step size of 5 numbers. If you change this to 3, the pattern follows. It includes every 3rd number in the sequence, so on and so forth. So range is just another handy built-in Python function that one should be mindful of. Now lists, just like strings, integers, floats, and booleans, it's a data type. However, lists are most similar to strings, as in, they share a lot of the same built-in methods, like length, for example. Do note that we can also index strings. To prove this, I will declare a string title is equal to, let's call this show title, is equal to Game of Thrones. If I asked you to grab the 3rd character in the string, the M, well, from what you've learned, G is at index 0, A is at index 1, and M is at index 2. Therefore, you can index it like so. Show title, square bracket, 2. We will print this, and the output is indeed the character M. Just like lists, we can also slice a string, such that if I wanted everything from M up until the very end of the string, 2 would be my start index, colon, and remember, if you omit the stop index, it's going to automatically assume that you want to grab everything beyond your start index. And if we run this, we get Me of Thrones. That is all for slicing for both lists and strings. Now we're going to use membership operators to determine if something is inside a list or string. These membership operators are in and not in. According to the documented definition, In evaluates to true if it finds a variable in the specified sequence, whether it's a string or a list. Otherwise returns false. In contrast, not in evaluates to true if it does not find a variable in the specified sequence, and false otherwise. Let's test this out. Inside of Jupyter Notebooks, I will set a variable months is equal to January, February, and March. Now I want to check, is June inside this list? So I will check if June is in months. If I print this evaluation, and then run the cell, it returns a value of false because June is not in this list. If I switch this to January, it returns true because indeed January is in the list. Vice versa, if you put not in instead of in, it would evaluate to false because we're checking if January is not in the list. Indeed, January is in the list, so this statement is false. The same concept applies to strings, so we'll cover that very quickly. Make a variable course is equal to Python crash course. I will check if the set of characters crash is inside the string. So, crash in course. Go ahead and print the return of this evaluation. And this evaluates to true because this set of characters is indeed inside of the string. Change this to rash, and it still evaluates to true because the set of characters rash is also inside the string. If I make this some random variable like A, B, C, D, obviously this is false, and vice versa for not in, because it is not in the string. That is all for membership operators. In the last few lessons, we went into a lot of depth when discussing lists, membership operators, and list methods. In summary, we discussed that lists are data types for mutable ordered sequences of elements, whereas tuples, just like lists, they are immutable ordered sequences of elements. They are used to store related pieces of information. Keyword related, and that information is enclosed in a parentheses. If two values are so closely related that you'll most likely always use them together, use a tuple. For example, back to Jupyter Notebooks, we will set a variable traits is equal to a tuple such that the person is tall, slim, and blonde. This tuple you see right here, it's similar to a list in the sense that in this case, it encapsulates an ordered sequence of strings where each of them can be accessed by their index. For example, you can set height is equal to traits at index 0 and build is equal to traits at index 1. We can go ahead and print height and build, and everything works out accordingly. Now, unlike lists, we cannot change tuples, they are immutable. We cannot add or remove elements from a tuple without creating an entirely new object. Oftentimes, parentheses are omitted when declaring tuples. If we omit them, everything should still work out the same way. They are completely optional, and it's up to you whether or not you want to keep them depending on if the parentheses are useful in clarifying the code. One last thing I want to demonstrate before we end this discussion is tuple unpacking. Before doing so, it's important to note that while we were successful in assigning all the elements of a tuple to multiple variables, there is a more compact way of doing it. That is, we could have simply used the comma notation to write height, build, hair, is equal to traits. This would respectively assign tall to height, slim to build, and blonde to hair. We can actually shorten this even further if we don't need to use the traits variable directly by setting height, build, and hair equal to tall, slim, and blonde directly, and deleting that. This is called tuple unpacking. It assigns the contents of our traits tuple to multiple variables without having to make multiple assignment statements. We're going to take a look at sets. There are many collection types at our disposal, and sets are one of them. The set data type, just like a list, is mutable, except in a set, elements are unique. What do I mean by this? Well, I'm going to create a variable, duplicate numbers is equal to 1, 1, 2, 2, 3, and 3. This list has duplicate numbers. What if we were to convert this to a set? Set unique numbers is equal to a set of duplicate numbers. Go ahead and print unique numbers. Going to make this into a plural. Run the cell, and it prints out 1, 2, and 3. By making this list into a set, it removed the duplicate elements from our list. Hence why a set is a collection of unique elements. This collection of elements is also mutable, meaning we can change it. Set has a built-in add method, which is similar to the append method that we saw earlier for our list. To our unique numbers set, we will add unique numbers dot add, and we will add the number 4. If we print the set now, print unique numbers, it should give us 1, 2, 3, and 4. It added that number. What distinguishes add from append is that if I try and add an element that already exists in a set, it won't actually add it, since a set is composed of unique elements. When I ran the cell and tried to add the number 3, indeed it didn't do it. That is pretty much all we're going to cover for sets. Just remember that sets are unordered, so we cannot use an index to represent the position of an element inside of a set. We can check if an element is inside of a set with the membership operator in. If you were to try and print 2 in unique numbers, such that we're checking if 2 is inside of the unique numbers set, it returns true because indeed it is a part of the set. There are many operations that can be done with sets. However, this is where we will conclude our discussion and move on to dictionaries. As previously noted, sets are mainly used to store unique elements, and talk about dictionaries, a much more flexible data type. Unlike regular sequences, dictionaries are composed of unique keys. Each unique key corresponds to a value. Even though dictionaries themselves are mutable data types, that is, we can add, change, or remove key value pairs as we please, the keys themselves that compose the dictionary, they must be unique and of an immutable type, either string, number, or tuple. Let's look at an example. In the Jupyter Notebook app, we'll declare a dictionary by setting a variable inventory is equal to curly braces. Dictionaries in Python are denoted by curly braces. Inside these curly braces, we'll have key value pairs, such that the keys will be grocery items and the value, the price of an item. So, bananas, they will have a price of $1.29, $1.29. Apples, they will be priced at $2.99 a pound, and papayas, $1.39. And there you have it, key value pairs. The key is an immutable string type, a grocery item, And the value in this case is just a number, a price corresponding to the grocery item key. Dictionaries are not ordered. If you remember with lists or tuples, they were indexed by a range of numbers. Dictionaries are indexed by their keys, meaning I can access a specific value inside of my dictionary by referencing its corresponding key. If I were to print inventory with key bananas and run it, I should get 129. Not only are dictionaries unordered, but we can also change their values. They are mutable. Let's assume the price of bananas went up. They are now $2.99 a pound. What I would do is access the dictionary value based on its key. So, inventory, bananas, and now I can change the price, the value corresponding to the bananas key, to make it equal to $2.99. After changing it, if I print inventory, bananas, it is indeed now $2.99. The value was mutated, it was changed. Dictionaries also have a useful built-in get method, which gets the values. It looks up the value at that specified key. If the key you specified doesn't exist in the dictionary, then it would just return none. Let's try it out. Make a variable, bananas, price, is equal to inventory.get. And I will get the price of the bananas. Print bananas price, and it would get the value of $2.99. Otherwise, if I put some random key, like strawberries, we'll declare a strawberries price variable. If I try to obtain a random key that doesn't actually exist in the dictionary itself, and print the results of this get method, it would bring me back none. We don't have a price for this yet. We can also check if something is inside of a dictionary. In our case, I want to check if we have a price for papayas. You probably guessed it, we need the membership operator in. So we'll print papayas in inventory. It will check if we have a key papayas inside of our dictionary. Run the code, and of course we do, it's right here. If I try out some random key, let's say celery, it returns false. In summary, dictionaries are an unordered set of key value pairs, such that every key must be unique. A pair of braces is used to denote a dictionary, such that the dictionary's main purpose is to store and extract values based on their key. That is all for dictionaries. Mutable. The Google definition is something that's liable to change, something that's changeable. Well, in this context, mutability refers to whether or not we can change something once it's been created. If an object can be changed, then it's mutable. If an object cannot be changed without creating a completely new object, then that would be considered immutable. This leads us to our next discussion. Lists and strings. We saw that they were very similar data types in the sense that they both share similar methods. However, they are distinct in many ways. Obviously, strings are sequences of letters, whereas lists can be sequence of any data type enclosed in brackets. However, a very subtle difference between the two is mutability. Strings cannot be changed. They cannot be directly changed, whereas lists can. So it follows that strings are immutable and lists are mutable. How can we prove this? Okay, let's start with lists. I will make a variable grocery list is equal to bananas, apples, and cauliflower. Let's assume that instead of cauliflowers, I want rutabagas. I can simply change the element at index number 2 to rutabagas. Simply enough, grocery list at index 2 equals rutabagas. Print grocery list, run it, and indeed the change occurred. Since we were able to change the list is mutable. However, let's try this with a string. Set a variable misspelled vegetable is equal to cucumber. Clearly, I misspelled the word cucumber. This O right here should be a U. Intuitively, what I would think to do is grab the character at index 0, 1, 2, and 3 and change the element at that index to a U. Let's try it. Misspelled vegetable at index 3 is going to equal a U. If we try to print misspelled vegetable, what will happen is that we're going to get an error. Strings are immutable. They cannot be changed. To change a string, you have to create a completely new string. Two things to keep in mind when working with data types. Are they mutable or not? Are they ordered or not? We saw an example of mutability and immutability when we spoke of strings and lists. We discussed how both strings and lists, they are both ordered. Every element or character is in a certain position, and the position of that element is represented by an index. And through the index, we can access that element or character. However, we still haven't worked with data types that are unordered. You'll see examples of unordered data types later on. For now, just keep these two thoughts in mind when working with data types. Are they mutable? Are they ordered? Why do we care if something is mutable or not? Let's talk about that. Previously, we concluded that strings are immutable, whereas lists are mutable. If you're still confused as to why that is, make sure to revisit that lesson. Anyways, how does that affect the behavior of the data type? If I create a variable name is equal to Amir, that variable holds an immutable string, which is saved in memory. If I assign other name is equal to name, and then reassign name to another value equal to John, this does not affect the value of other name. We can show this by printing print name and print other name. In the results, you can clearly see that even though we updated the value of name, that update was not reflected in other name. Other name retained the initial value of Amir. However, what if we're dealing with a mutable data type? Would we see a different behavior? If we change the data type, well, yeah. Otherwise, what's the point of this video? What we'll do is we'll set books is equal to the Catcher in the Rye, the Mist, and Lord of the Rings. If I set more books is equal to books, and then change one of the books in my list to, let's say, A Song of Ice and Fire, that is, books at index 0, we're going to go from Catcher in the Rye to A Song of Ice and Fire. If I go ahead and print books at index 0, indeed, it equals A Song of Ice and Fire. The list changes such that the element at index 0 is now A Song of Ice and Fire. What if I also printed more books? Print more books. Initially, we set more books to equal books, which held this value, the Catcher in the Rye, the Mist, and Lord of the Rings. But then we updated the first index in our books list. Will that change also be reflected in more books? Let's test it out. Run the cell, and indeed the change is reflected. The take-home message being, since a list data type are immutable, changing a list will reflect in all variable names for that same underlying list. Either variable, either name, either label, whatever you want to call it, can be used to change or access that list, all of them holding a reference to it. So that's it for the behavior of mutable and immutable data types. It's very important to be mindful of their subtle distinction, what we just talked about in this video, so that you're always aware of how data is being accessed and configured in your program. Always double check your work and use the print function to make sure that data is being configured the way that it's intended to be. And that concludes our discussion on behavior of mutable and immutable objects. In the next video, let's continue our previous discussion on built-in list functions. Run the cell, and the output, as expected, is 4, since that is how many elements we have in this list. Another function useful for lists is the max method. Max will return the greatest element in that list, in this case 7. We'll test this out by writing max, and the argument will be the numbers list itself. Indeed, it returns 7 because 7 is the greatest numerical value in the list. However, what if I had a list of strings? How would max then work? Well, we can make a list names is equal to whatever names you want. I will stick with Thomas, Geo, and Zach. By taking the max of this list, that is max names, the output of this is Zach. Why? When dealing with strings, the maximum would be the string that appears last based on alphabetical order. So we can conclude that max works differently depending on which data types you have inside of your list. What if the list contained not just strings, but also numbers? What we'll do is we'll put a 1 in there. In this case, the data types are incomparable. If you try to run it, the result cannot be defined, and as such, the error is shown. Let's revert this back to just having strings and use the min function. Min in this case will do the exact opposite of max. It will return the string that shows up first based on alphabetical order. In our case, GO, since G falls before T and Z. Intuitively, for a list of integers, min would simply return the smallest integer, in this case the number 3. The same idea follows for floats. Another useful function that we can use for lists is sorted, such that sorted will take in a value and argument of our numbers list. If you run this cell, the output is a copy of a list that's sorted from lowest number to highest. By doing the same thing for our names list, sorted names, what this will do when ran, it clearly sorts our names list in alphabetical order, Gio, Thomas, and Zach. We've talked about functions. Now let's talk about methods. Remember, we said that functions accept arguments or argument inside of their parentheses, as you can see right here. This is a function. A method differs from a function in the sense that every data type has its own distinct set of methods. We'll start off by looking at the join method. The join method is actually a string method that takes in as an argument a list of strings. From the string argument, what it's going to do is return a string consisting of every element on that list. All of these elements joined by the string that's calling the method. Here's an example. We'll start off with a hyphen, a string hyphen, which calls the method join, .join, which takes in as an argument, remember, a list. We will have a list of strings. January, February, and March. If we run this code, what it just did is it joined every string in that list with the hyphen string that called the method. Instead of a hyphen, you can make this into a blank space, such that now every string is joined by a blank space. The list of strings is converted to a string such that every element is joined by the separator string calling the method. In this case, the separator string is just an empty space. Another useful string method is format. This is most easily demonstrated with a print statement. So print, this person is, open up curly braces, close curly braces, do that once more, and another set of brackets. Okay. What we can do now is we can format the string, .format, such that wherever there's a bracket, or a curly brace I should say, we want to replace it with a specific string. That is, inside of format, I can write tall, slim, and blonde. If I run this code, we get the person is tall, slim, and blonde. The string was formatted such that each string over here was assigned to each curly brace according to the order in which they were written. Another useful method is the append method. If you've worked with arrays in other languages, you've definitely seen this method before. What it's going to do is add an element to the end of a list. So we'll copy and paste the list that we have over here and set it equal to a variable called months. Months is equal to the list of strings. What we can do now is append a new month to the end of our list. That is months.append, and we're going to append the month April. We'll go ahead and print months, and we get our appended list, January, February, March, and April. Perfect. There are many more methods and functions that we can talk about. However, this is where we conclude our discussion on lists. If you've ever programmed before, you've seen the if-else statement. It executes a block of code if a certain condition that you specified evaluates to true. If it's not true, if a specified condition is false, then the if statement will skip the code. This is very important. An if statement runs or skips code based on its conditional statement. You never want to run code in a top-down approach. Some code should only be run based on existing conditions. Otherwise, it should be skipped. Let's have a look at an example. Remember this dictionary we had earlier? We used it to identify the price of each grocery item. We also talked about the membership operator in, and how it can check if something is inside of a dictionary or not. So what we'll do is we'll declare a string item. For now, it will just be Brussels sprouts. And now we'll check if item in grocery items. If the item is inside of our dictionary, then we want to execute some code. For now, I'll just print found the item. There's one thing here that's very important and that I want to point out, and that is the indentation. In most programming languages, indentation is just a way for your code to look more readable. In Python, however, instead of using brackets to indicate scope, indentation is required to indicate what block of code a statement belongs to. In this case, the print logic, because it's indented in such a way, it belongs to this if statement. Notice how when we press enter after the if statement, it creates that indentation for us. In summary, much of your code's logic will depend on white space, so be careful how you indent your code. If we were to run this code, nothing gets called. Why? Well, the item is not inside of our dictionary. We don't have Brussels sprouts in there. This if statement evaluated to false, and it skipped this block of code. Although we need to let the user know if it skipped it or not. So we'll add an else statement, such that if this if statement evaluates to false, this code is skipped, and the code belonging to the else statement will then get called. In else, we'll print could not find the item. And there you have it. We can actually take this one step further, such that in the else statement, if the item does not exist in our dictionary, which it doesn't, we'll update our dictionary to have the item. That is, grocery items dot update, and we'll add a new key value pair. To do that, make sure to write your curly braces to indicate it as a part of the dictionary. The item that's passed in is going to be the key, so Brussels sprouts, and we'll give it a default price of $2.99. We're not too concerned with the price at the moment. And right after updating the item, we'll print just added the item. Here is the updated grocery list. And we'll pass in our grocery items dictionary. Run the code, and it works out as expected. The item at first is not in the dictionary. This if statement evaluates to false, so its block of code is skipped. The else statement then gets called, adds that item to our dictionary, and prints out the following statement. What I want you to take away from this video is not so much dictionaries, but conditional statements. To summarize, if statements evaluated whether or not a statement is true. If it is, it invokes a certain block of code. If not, the code inside of the else statement was triggered instead. Now we'll look at elif statements. Let's assume that an if statement fails, yet we're still not ready to move on to the else statement. We want to test one more condition, or a few more conditions. And if those conditions are true, we want to invoke a separate block of code before moving on to the else statement. That's where elif comes in, and we'll make use of it momentarily. Let's continue on from our previous lesson, and instead of just setting item equal to Brussels sprouts, actually we'll change this from Brussels sprouts to rutabagas, and we'll set a price for rutabagas equal to $2.99 on the same line of code. If you're not familiar with this notation, please refer back to section 1 of the crash course. The way this code is currently set is that if an item is not in the dictionary, the if statement is false, the else clause is true, and it updates the dictionary with that new item. And you know what? Instead of setting $2.99 directly, we'll set it equal to our variable price. What we'll do now is we'll add an elif statement. Elif price is bigger than $2.99. We want to tell the user, or in our case, we'll just print too expensive for inventory. If we run this, clearly the else statement still gets called because rutabagas is not in our grocery list and the price is clearly not bigger than $2.99. I'm going to rerun the first cell to restore the initial value of grocery items, and now I'm going to increase the price of rutabagas. Rerun the code. First of all, the if statement gets skipped because this condition is still false. Rutabagas is not in the initial value of our grocery items dictionary. However, this evaluates to true because the price is indeed bigger than $3.99. Because the price is so expensive, we're not going to add it to our inventory, thus the elif statement gets called. This evaluated to true and ran the block of code corresponding to the elif statement. This is also the first time we've made use of a comparison operator inside of an if statement, or an elif statement for that matter. There are other comparison operators like equal equal, is not equal, bigger than, which we just saw, smaller than, greater than or equal to, and smaller than or equal to. The names of these operators kind of gives away their functionality. Let's look at one more example where we can make use of the is equal comparison operator. We'll start on a new cell and create a variable named daytime is equal to dawn. And what we'll do now is we'll write if daytime is equal to dawn, make sure there's two equal signs, not one, in order to indicate a comparison operation, not an assignment. So if daytime is equal to dawn, then we're going to print still asleep. Note the indentation to make sure that this block of code belongs to this statement. Elif, else if, daytime is equal to morning, then we'll print time to go to work. Elif, daytime is equal to noon, we'll print time to take a lunch break. Elif, daytime is equal to afternoon, print time to go home. And finally, we'll put an else statement. So if it's none of these daytimes, it could be nighttime, midnight, whichever, we'll simply print time to go to sleep. So the purpose of this exercise was not only elif statements, but also for you to remember to use double equal signs when making a comparison. Do not ever confuse the double equal sign comparison operator with the single equal sign assignment operator. If you want to make a comparison, as we are doing here, use a double equal sign. If you wish to assign a value to a variable, use only one equal sign. It's very important to be able to distinguish between the two. Let's end this tutorial by running our code, and it prints still asleep. Since this if statement evaluated as true, this block of code is run, and all of these ones are thereby skipped. If I change this to noon, run the cell, this block of code is skipped, and now this is ran because this evaluates to true. If I change this to nighttime, none of these get called, and this gets invoked. Before I end this tutorial, I really want to stress code indentation. It's how we tell Python what code is inside the if statements, and what code is outside of it. This code is indented such that it corresponds to this if statement, so on and so forth. Indentation convention typically follows 4 spaces. Whatever amount of spaces you're using, it's important to stay consistent throughout. Otherwise, your code will have a different meaning than what's intended. Indentation applies to more than just if and else statements. However, things can get a little more complex than that, depending on your program's functionality. Let's have a closer look. To start this off, let's introduce something called Reynolds number. When studying the flow regime of some fluid inside of a pipe, if the Reynolds number is between 2,000 and 10,000, this flow is transitional. If it's under 2,000, the flow regime is laminar. If it's over 10,000, it's turbulent. We're going to focus on the transitional part of the regime. Back to Jupyter Notebooks, declare a variable Reynolds number is equal to 5,000. To check whether or not this value corresponds to transitional flow, we're going to use multiple comparison operators. That is, if 2,000 is smaller than the specified Reynolds number, whatever that may be, and if it's also smaller than 10,000, if Reynolds number is between 2,000 and 10,000, we're going to print flow regime is transitional. And that is it for using multiple comparison operators. To check if a value is between 2 other values, and all of that done inside of a single if statement. You'll come across situations like this quite often. If we run the code, indeed this flow is transitional since it lies between 2,000 and 10,000. Now if I change it to something that exceeds the range, for example 11,000, the if statement returns false. It does not lie between the specified range, and this code is therefore not invoked. This could have also been done with a logical operator. Instead, we could have written if Reynolds number is bigger than 2,000 and Reynolds number is smaller than 10,000, print flow is transitional. In this case, the Reynolds number must be greater than 2,000 and also smaller than 10,000 for this to return true. If one of these is false, if one of these evaluates to false, then the whole statement is false and this code is skipped. If we run the cell, clearly the code is skipped because this condition is not satisfied. 11,000 is not smaller than 10,000. Let's change this back to 5,000. I'm going to rerun this cell, and we're back in business. It satisfies both conditions of it being bigger than 2,000 and smaller than 10,000. Note how both if statements have the exact same results since they specify the same conditions, but just in different formats. Another operator that's often used is the OR operator. The OR operator, as we've seen previously, unlike the AND operator, only one of the conditions has to evaluate to true. So what we'll do, inside of a new cell, we'll write if Reynolds number is smaller or equal to 2,000, or Reynolds number is bigger or equal to 10,000, then we can say print flow is not transitional. I'm going to change Reynolds number to 1,000. Rerun everything, including the cell. Clearly the code is invoked because this condition is satisfied. It returns true, whereas this one is not. However, with the OR operator, only one of them needs to be true for the code to be invoked. This makes sense in our case because the Reynolds number is smaller than 2,000, meaning that it's laminar and thus not transitional. If it's bigger than 10,000, it would be turbulent and also not transitional, as this condition would then be satisfied. So long as one of these conditions is true, with the OR operator, this code is going to be invoked. That sums it up for complex Boolean expressions. You learned all about if, else, and elif statements, as well as how to integrate logical and comparison operators into these statements. We will now expand our discussion on control flow by covering loops. There are two kinds of loops in Python, the for loop and the while loop. We'll start this off by using the for loop. A for loop can iterate through over any iterable. What is an iterable? Well, as the name suggests, anything that we can iterate through, anything that can return one of its elements at a time. That includes lists, strings, dictionaries, tuples, etc. We'll start our example by iterating over a list. In Jupyter Notebook, declare a list months is equal to January, February, and March. We can iterate through this list by using a for loop. That is, by writing for month in months. So for every month inside of our months list, we're going to print the month. This variable month corresponds to the month inside of our list that's currently being iterated through. If I run the cell, clearly it looped through our entire list, and one at a time it printed January, February, and March. Notice how this line of code is indented, and that's because, just like how we had it with if statements, this corresponds to the body of the for loop, such that this indented block of code is invoked once for every single element of our iterable, and each element, at the moment that it's being iterated through, is represented by an iteration variable that we explicitly declared to be called the month. You can name your iteration variable anything you like. A common recommended pattern is to name it something that's singular to our list, as we did here. We can also iterate through a range. We saw ranges in the slicing video when we learned how to create a list from a range of numbers. Well, we can iterate through a range of numbers by simply writing for number in range 0 to 100. And then we're simply going to print all the numbers from 0 to 99. That is, print number. Run the code, and clearly it iterated through our entire range, and one at a time it printed 0, 1, 2, 3 all the way till 99. And each number, at the moment that it's being iterated through, is represented by the number iteration variable when it's being printed. So far we looked at two iterable types that we can loop through, ranges and lists. Do note that we don't always have to make use of our iteration variable. You can print something like hello, for example. It doesn't matter. For loops so far, we've used them to extract elements. We can also use them to create elements. We'll demonstrate this by creating a variable, names, is equal to a list. My list will be Hillary, Diana, and Brian. Our end goal is to capitalize all of these names. We're going to modify this list with a for loop. To start this off, a common way to modify lists is with the range function. So what we'll do is we'll iterate through the range of this list and grab the index of each element. So we'll write for index in range, and the range will have our list length, and the argument will be the names list. The range will be the length of our names list. If you remember from before, range takes in a start index and a stop index. In this case, all we put in was a stop index, which right now equals 3, the length of our list. Since we omitted the start index, Python will assume a start index of 0 that goes all the way till 2. Why 2? Why not 3? The length is 3. Remember, the stop index is exclusive, meaning that the range will stop at the number that's previous to it. Therefore, the range will go from 0 to 2, which matches the indices on our list, 0, 1, and 2. If you're not too sure how start, stop, and step works, make sure to revisit the slicing lecture. Anyways, if we print index, indeed the result given is exactly what's predicted. We can actually use the index of each element to point to that element that's in our list and capitalize it. To do so, write names index is equal to names index dot title. The method title returns a copy of the string in which first characters of all the words are capitalized. So in the first iteration, the index is 0, which means that we're pointing to the first element in our list, Hillary. We're going to modify the first element of the list to make it equal to a capitalized version of Hillary, thanks to the title method. This loop is then going to iterate twice more and do the exact same thing for Diana and Brian. After the for loop, once you're done modifying the list, we're going to print names. Notice how there's no indentation here, because this print statement will occur after the for loop. It doesn't belong to it. Let's run the code, and there you have it. It iterates through the list 3 times, capitalizes each element, and then prints the updated version. That is all for looping through lists. We're going to apply the same concept by iterating through a dictionary. There are 2 ways to iterate through a dictionary. The best way to demonstrate it is to actually dive right into it. And inside of Jupyter Notebooks, declare a dictionary, movies, which will equal, open up curly braces, Titanic. And Titanic, I believe, was released in 1997. As well as we'll have another entry of Finding Nemo, another key value pair, which was released in 2003. If you don't know what a dictionary is by now, please refer to the dictionaries tutorial in part 1 of this crash course. Anyway, looping through dictionaries is different in the sense that there are two ways of doing so. You can iterate through just the keys or both key value pairs. Iterating through just the key is done like so. For key in movies, print key. If I run the cell, it iterates through our dictionary, and one at a time it prints the keys, such that each key in our dictionary is represented by a key iteration variable that we explicitly declared. If you want to access both key and value, simply add another iteration variable. You can call it whatever you want, although best practice is to just call it value. There is still one more step if you wish to iterate through both keys and values, and that is to use the built-in methods items. Like so. We need items since it returns a list of the dictionary's key value tuple pairs. So go ahead and print value now. Run the cell, and clearly it outputs both key value pairs. We can actually get a little fancier than this by using the string format method. If you forgot what format does, first we'll declare a string inside of our print statement, and that string will be the movie, open up curly brace, close curly brace, was made in another set of curly braces. What we can do now is we can format the string .format such that the first bracket will be replaced by our key and the second bracket will be replaced by our value. Run the code and it iterates through every key value pair for each one, printing a distinct sentence. That is all for for loops. While loops are different than for loops, in the sense that the amount of times a for loop iterates through a certain iterable, it's predefined. If we're looping through a list of 3 elements, then we know the amount of times the for loop gets invoked is 3 times. However, while loops are different. While loops have an indefinite amount of iterations, in the sense that the amount of times a while loop will iterate through a block of code depends on your code's logic and whether or not a certain condition is met. If you're not careful, the while loop could go on forever. So, rule of thumb, a for loop iterates through an iterable, and a while loop iterates based on a condition. While a condition is true, the while loop will invoke its block of code repeatedly until the condition becomes false. In Jupyter Notebook, I'm going to declare a variable, random number is equal to 20. Subsequently, declare that while random number is smaller than 30, then print random number. Once again, notice the indentation, which indicates that this print function belongs to the body of the while loop, just like we saw with for loops and if statements. If I run the code right now, it's going to get executed forever. Why? Well, this condition is true no matter what. 20 is always smaller than 30. We're not doing anything in the body of the while loop to change this value. So this condition will always be true. Let's go ahead and restart the current kernel we're going to shut down the kernel. Comment out this block of code with the keys Command/. We will restart our kernel and run all the cells. So now, inside the body of our while loop, let's uncomment our code, and inside the body of our while loop, we'll specify it such that for every iteration, we'll increase the value of our random number by 1. That is, random number plus equals 1. Remember the plus equals assignment operator. It takes the current value and increments it by 1. So for every iteration, we'll increment our number by 1 until it reaches 30, until the number becomes big enough for this condition to be false. Run the code, and it iterates through our code 9 times, incrementing our number 9 times. Once the value becomes 30, clearly the condition is now false. This code will not be triggered for that value and the loop breaks. That is it for while loops. We determine that for loops will keep iterating based on the range of the iterable, whereas the while loop keeps iterating through a block of code until its condition stops being met. We can actually have more control over our loops with the break and continue keywords. The continue statement jumps over one iteration of the loop. It skips one iteration of a loop, whereas the break keyword jumps out of the loop completely. It terminates it. If we detect that a certain condition has been met and we don't need to iterate through our code anymore, then we break out of the loop. Let's look at an example. We'll start off by making a list number, a list of numbers, is equal to a list which ranges, we're going to have a range from 0 to 10. You should know what this is by now. Simply a list of numbers that goes from 0 to 9. If you're not sure why, make sure to revisit the video on slicing. We'll print this list for clarity. Print numbers. There's our list. Now on the second cell, we're going to loop through this list with a for loop. For number in numbers, and inside of our block, every time we iterate through this list and access each individual number one by one, we'll declare an if statement. So, if number modulus 2 is not equal to 0, if our number divided by 2 does not give us a remainder of 0 if the number is odd, we're going to continue. And outside of the if statement, we're going to print the number. The logic being, if we're looping through an odd number like 3, this condition will evaluate to true since the modulus will not be 0. Continue gets invoked and skips over the loop, and nothing below gets called. Otherwise, if we're iterating through an even number, a number like 2 or 0, continue is not invoked as this would evaluate to false. It does not skip over the loop body, thereby printing the number itself. If you run the cell, indeed we end up getting 0, 2, 4, 6, and 8. Since every time we iterate through an even number, it skips over the continue keyword, therefore executing the code inside of the for loop body. If we replace this with a break keyword, as soon as we iterate through an odd number, it would just terminate the entire loop. Run the cell, and clearly it first iterates through 0, an even number. This condition is false, break doesn't get called, and the iteration goes without interruption, printing the number 0. But then we're iterating through the number 1, that's an odd number. The if statement evaluates to true, breaking the entire loop. The same concept applies to while loops. So we're going to cover all things functions, and while previously we made use of built-in functions, it's important to distinguish that a function is a named section of your program that performs a specific task. That way, when you want to execute a specific task, all you have to do is call the function. This highlights one of the most important reasons that programmers use functions. Reusability. Once a function is defined, it can be used over and over again, without having to worry about any of the specifics needed to accomplish the task. This will be a lot more clear once we dive into it, but that being said, we'll learn all about functions, scope, docstrings to document our functions, and finally we'll also look at anonymous functions with lambda expressions. So we're going to discuss functions. Functions, as per the official definition, represents a section of your program that performs a specific task. One of the main reasons why functions are so useful is reusability. Once a function is defined, it can be used over and over and over again. Without having to constantly copy and paste your code, you can simply call your function. You can invoke the same function many times in your program, which saves you a lot of work. How do we define a function? Simple. To define a function, start with the def keyword. As in, we're defining a function. We're declaring a function definition. Then comes the name, the function name. I want to define a function that calculates the area of a rectangle. So I'll call it rectangle area. The area is dependent on length and width. So immediately after the name, you would put parentheses that include these arguments, length and width. The arguments, the length and width, are passed in as the function is called, where they can then be used inside of the body of the function. Let's dive into Jupyter Notebooks to see this in action. As previously noted, the first step is to obviously declare the function definition. We'll start this off with the def keyword. The function name will be rectangle area. Next comes the parentheses, which in our case is going to take in 2 arguments. Functions don't have to take in arguments, but we will have 2 of them that are length and width. We discussed this previously. And just like if statements as well as loops, to open up the block of code that corresponds to our function, we need a colon, followed by indentation. Any code within the indented space belongs to the body of the function. And what we'll do is, inside the body, we're going to set a variable name area is equal to length times width. Misspelled width. Whatever length and width that the user inputs when they call the function, they will be multiplied to obtain the area. And now all we have to do is simply return the area. Return area. We can actually do this in a single line of code by directly returning length and width and getting rid of this line. Very concise and, more importantly, reusable, because now I can simply call the function like so. On a new cell, I will call the function rectangle area. The length will be 2 and the width 3. If we print the value of our function call, the return value, what it's going to give us is the area. Run the cell and it prints 6. In essence, we called the function rectangle area, passed in our length and width as arguments, which were evaluated inside the function definition, and returned a value of their product, which was 6, thereby printing this return value. If you've ever programmed before, this should be very familiar to you, aside from the change in syntax right here. Before wrapping up this video, we can actually print the area directly inside the function. We don't actually need a return value. We can do so by first deleting this print statement here, delete the return statement, and we're simply going to print inside of our function definition length times width, the area. If I call the function again, rectangle area, this time I will pass in the same length and width, 3 and 2. The arguments that were passed in are multiplied and printed. This function obviously is reusable, so we can call it as many times as we want. I will copy and paste this function call 3 times. Let's print the area of a 4 by 6 rectangle, a 3 by 9, and a 2 by 2. Run the cell, and we get 24, 27, and 4. Perfect. All of the areas that were required. That is all for function definitions. Obviously, the logic can be a lot more complex than that. We can have all kinds of if statements and loops going on in here, but the main idea that I want you to take home is that this is a reusable chunk of code that accomplishes a specific task. We cannot talk about functions without talking about scope, whether it's Python or any other programming language. A scope, as per the official definition, in any programming language is a region of the program where a defined variable can have its existence, and beyond that, the variable cannot be accessed. In this lesson, the local variables will be function scoped. That is, variables created inside of a function, they can only be accessed within the block in which they are declared. A global variable, however, can be accessed in every part of the program. Back to Jupyter Notebooks. If I define a function, def random function, with no arguments, and inside the function I create a variable, name is equal to Bill. That variable name that we created inside the function can only be used within that function. It is scoped to this function. Accessing it outside the function is not possible. If I try to print name outside the function, we will get an error. Name is not defined. It is only defined within the scope of the function. On the other hand, we talked about global variables. If I declare a variable number is equal to 2, the number variable can be accessed anywhere. It is not scoped to any function. It is global scoped. If I print number, everything works out fine. We concluded that the benefits of having that function was that it's a reusable chunk of code accomplishing a specific task. Because the function is reusable, whenever we want to calculate the area, instead of writing the formula down over and over, we can simply call the function rectangle area as many times as we want, and thereby calculating the area for as many dimensions that we choose to specify. This is a very simple example. However, when your code gets larger, you're going to have a lot more functions, and oftentimes you'll be working with a team of developers. To them, it won't be clear what the purpose of your functions are. That's why docstrings can be used. Docstrings are a type of comment used to explain the purpose of a function and how it should be used. It documents your code. Back to Jupyter Notebooks, to declare a docstring, you must declare triple double quotes, like so. In between the triple quotes, you can now write anything you want, whatever you feel best describes your function. The rectangle area function is very simple, so I'm just going to write calculates area of a rectangle. However, if you're dealing with a more complex function, sometimes a longer description is more appropriate. If you want to get super descriptive, a more common convention is to explain a function by using the input and output descriptions. The input in this case would be like so. Input. This function takes in two parameters, length and width. And the output would be this function calculates the area based on the length and width provided by the user, where area is equal to length times width. We may have went a little over the top in explaining this very simple function. If you want to do it the way we did it previously with a single sentence, that's perfectly fine as well, so long as you think it provides sufficient documentation. We'll finish our discussion on functions by first going over higher order functions. A higher order function typically is a function that takes in another function as an argument. Let's have a look at a very common higher order function, the filter. Back to Jupyter Notebooks, declare a list of numbers is equal to 1, 2, 3, 4, and 5. Alternatively, I could have used the range function to create this list, but regardless, what we want to do is filter out any number that's odd. With your current knowledge, you could use a for loop, iterate through this entire list, check if the number is odd with an if statement. If it is, remove it from the list based on the index. We did something very similar to this before when we modified lists based on for loops, but that would be a little tedious and not very concise. There is a much easier way, and that is to use the higher order function filter. What we'll do is we'll write filter to denote the filter function, and the first argument of this filter function is, guess what? Another function, which makes sense since we're dealing with a higher order function. More specifically, it takes in a function that returns a Boolean. So what filter will do is it will go through every single element of our list. For every element that it iterates through, it's going to pass it into our function. In our case, the function will evaluate whether or not the number that's being iterated through is even or odd. If the number is indeed even, the function will return a value that evaluates to true, telling the filter function, hey, we're going to keep this value. Otherwise, if the number that's being iterated through is odd, the function will return a value that evaluates to false, telling the filter function, filter out this number, get rid of it. Now that we went over the theory, let's execute it. We're going to make a function, def, even, or odd, which takes the number that's being iterated through. We're just going to call it number. That's the argument, and that function will return number modulus 2 is equal to 0. Make sure this is a double equal sign since we're declaring a comparison, such that we want to check if the number being iterated through, is it even or odd? If it is even, it will evaluate true and it will tell the filter function to keep the number in the list. Otherwise, it will evaluate to false and the filter function will know to remove the number. Obviously, the next step is to actually invoke this function inside of filter, even or odd. And careful, do not specify a parameter inside of the filter function. The second argument of the filter is the iterable that we want to filter from. In our case, the list, the numbers. Finally, we just have to convert this back to a list by enclosing it with a list type. And if we print this, run the code, it outputs 2 and 4. It removed all of the odd numbers. It iterated through every number in our list, and for every iteration, it checked to see if that number divided by 2 doesn't give a remainder of 0. Is it even or is it odd? If it was odd, if the remainder was not 0, the function returns false and the number is thereby filtered out. And we get our even numbers. There's one problem with this. Remember what we talked about earlier. Functions should be reusable chunks of code. If you're just going to use it as an argument in a higher order function, it's not really reusable. That's why in this case we use the lambda operator. The lambda operator provides a way to create small anonymous functions, functions without a name. They are helpful for creating quick functions that aren't needed later in your code. How do we create a lambda operator? Well, first we need the lambda keyword, lambda. We need the lambda keyword to indicate that this is a lambda expression. Following lambda is the argument that's passed in from the higher order function. In this case, we'll just call it number. Similar to functions as well, following that is a colon. And finally, what comes next is the expression that's being evaluated and returned. In this case, we're returning a Boolean expression that checks whether or not the number being passed in from the filter function, is it even or odd? If it is even, it evaluates to true, otherwise false. So just copy and paste that, and we should be good to go. Notice how we don't need to specify a return value inside of a lambda expression. This is much more concise. If we delete this, run our code, we get the exact same results. This acts the same way as our regular function did. There are obviously a lot of higher order functions in Python, like map and reduce. But for now, I just want you to keep in mind that although lambda expressions are not ideal to replace complex functions, they can be useful for short, simple functions.